I've been working my way through all of Heathkit's basic power supply designs, doing a series on them, and it's time for another one. Once again, I'll start with Chuck Penson's excellent book on Heathkit test equipment products, and I've already covered several of these models. I've covered the IP-18 and its essentially identical replacement, the IP-2718, which is right there. I've covered the IP-20 in a peripheral fashion. The IP-20 and the IP-27 are essentially the same power supply, just reformatted with a different case and one component replaced with a different type, but essentially the same power supply. So I had an extensive restoration and documentation video on the IP-27, so I figured that covers the IP-20. In the course of doing that, I've recently done the IP-28, talked about its history, done a restoration and full description video. I have an IP-2700 series which accounts for most of the Heathkit models. They're all representative of the same type. I'm working on that one. And there is only one more model, and that's the last Heathkit power supply model, the IP-2718. And I should say once again, like I did on my other videos, these are only the Heathkit low voltage regulated power supplies. They did have high voltage supplies for working on tube circuits, and they had some specialized power supplies for for some of their low cost test equipment to power the test equipment, and things like that. But just as far as power supplies intended to be used on electronics workbenches, these would be all the models. So the IP-2718 was introduced in 1976 and was made through 1990, so a pretty long-lived power supply, and they made tons of them. As it says here, it's a sophisticated upgrade of the IP-28, but in reality the circuits bear not a lot of resemblance to each other. They do have some commonality of circuits. They're both regulated linear power supply circuits using the technology of the day, so they do have some similarities. But there's probably more differences than there are similarities when it comes down to it. Heathkit called the IP-2718 the tri-output supply. It's the only one they made, really, that supplied multiple voltages at the same time. It essentially replaced three power supplies that could be sitting next to each other in one box. The unit provides a fixed 5-volt supply at 1.5 amps for powering logic circuits, and at the time it came out, logic circuits tended to be TTL circuits, so they tended to suck a lot of power, and it wasn't unreasonable to expect you might need over an amp of power to power, say, a breadboard or something that you're doing with all TTL logic. So that really made sense. Not like today when you can power a ton of CMOS stuff, you know, off of a couple batteries. It wasn't the same. Plus there were two 0 to 20 volt outputs, each capable of up to 500 milliamps. The 20 volt outputs can be set independently from each other or track each other. And that's a little bit misrepresenting what it actually was. They couldn't track each other. One of them could track the first one. So you could track one way but not the other one. They could be run in series or parallel. They're all isolated internally, and that's total galvanic isolation. So they are truly independent supplies. Therefore, you could actually wire the 5-volt supply in series with the 20-volt supply, in series with the other 20-volt supply, and get 45 volts if you wanted. Or you could set both of the adjustable supplies to 5 volts and parallel those with each other and with the 5-volt supply, and get up to 2.5 amps at 5 volts if you wanted to do that. A switchable front panel meter monitors voltage or current of all outputs. Load regulation is pretty good at less than 0.1% change from no load to full load on the 20 volt supplies, and 2% on the 5-volt supply. All outputs are short-proof, having built-in current limiting and or power output shut-off features integral to the design. This is really one of the last surviving Heathkits, even when they were shutting down the Heathkit kit business and switching over to more educational products that weren't kits and other ventures. This is one of the last kits that they continued to produce right up to the end. 4.5 inches high, 10 3/4 inches wide, and 9 inches deep, weighing in at 10 pounds. I'm making a few case modifications. First off, when I received this, it had been very badly packaged, and it had been banging around inside of the box. It didn't actually get scratched up from it, but something had been kind of stove in on the side of the box and pushed the meter completely out of its cutout in the case, and it was kind of sitting back here and down, and this aluminum bracket that holds it in by fitting into a slot here and going behind the shaft of the selector switch, or around the bushing of the selector switch more accurately. That was all twisted up, so I actually made a new one. It was just too hard to get the old one straight, so I just cut up some 1/16 inch aluminum and bent it the same shape in my bending brake, and it works just fine. I also noticed that the neon lamp on the front, even though the lens was okay, something had broken there, and the wiring and the neon bulb was actually floating around back here in the case, and whatever was holding the neon lamp into its red lens was dislodged, gone, or whatever. So I first tried to just glue something with super glue across the top of the red lens to hold it in, and it wasn't working. So I decided to try this bit. It's removable. I just bent up a aluminum bracket that pushes against the leads, which are insulated, so that the lamp doesn't want to come backwards and fall out of the holder. And I just tacked it to the bottom of the case with a bit of super glue. If I decide I don't like that approach, I can break that off there with a little bit of force, and I could put a screw through there to hold it down or do something else, but that's my current solution. The other thing is that the top case was damaged, and I had quite a time straightening it out, and it was missing most of the bolts or screws that hold it to the case, and they were oversized. I don't think they were the original ones, to the point where I can't put the original screws back in. They're a little too loose. So I decided the holes that remain were still just about the right size that I could use as a tap size for 632 screws. So I'm going to try that first, drill them out just a touch, and then tap them for 632, and I have some nice black anodized button head hex drive screws, which will look very much like the original ones. Okay, I've got my little hex drive black anodized button head 632 bolts, or screws if you will. Put them into my newly tapped holes. Looking good so far. And on the other side, put those on. Come on, get coordinated. Okay, gotta love my Chapman set. One of my favorite tools. So first, the restoration of this power supply. When I bought it on eBay, it was supposed to be working, but I don't think it was tested out very much more than just to make sure the meter moved and that the power came on. So I went over it pretty thoroughly, and I found just a couple of things that were wrong with it. The shaft on this potentiometer is bent, so the knob wobbles a little bit. It's not the knob that's on crooked, it's the actual shaft is bent. It must have been banged at some point, but it turns freely, so there's not much I can do to fix that. This switch is pretty stiff, but it's not gummed up, it's just the way the switch is. These were all pretty boogered up, but I have some other old pieces of Heathkit test equipment that used the same terminals, and I've dismembered some of those before because they were just totally wrecked, and threw the salvageable parts in my junk box. So I harvested those and put all better condition thumb screw caps on all of these. The switches on here were fine. I didn't even have to put any deoxit in them. It was pretty clean. I just went over it with some isopropyl alcohol. I mentioned elsewhere in this video that the meter had been pushed into the case and its bracket was done, so I remade the bracket. The bracket has a side effect of engaging with the anti-rotation tab on the switch so that it keeps it from twisting. I'm pretty sure that's a deliberate decision on Heathkit's part to make the bracket the width that it would engage with that. It's the only time I've seen Heathkit do it that way. I did check out the capacitors. They're all name brand capacitors like Nichicon and ICC. I don't know when this one was built because, again, they made these through 1990. The serial number is, somebody must have been rubbing away at the serial number tag, and the serial number does survive, but I couldn't find any method to trace its age based on that. Anyway, just some basic tests and observations of these caps suggested to me that they're still in good enough condition, and I have an identical supply like this at my office where I work that we use on our test bench, mostly to simulate current loop power supplies when we're testing transmitters and so on, but also powering up other things from time to time. And I've been observing it and testing it over the years. I think we put that one together in '86, and other than a couple of things that were damaged just in all the handling and use it got over the years, it hasn't suffered in performance any, and every once in a while I would hook up a scope to it and take a look at the waveforms and see if the ripple had increased or anything that would indicate aging of the capacitors, and they all seemed fine. So this is one of the few Heathkits I'm restoring where I'm not planning on doing anything with the capacitors. The linear voltage regulator IC, which is used for the 5-volt power supply, is working on this one. The other one that I have at my job, that transistor died, or not transistor, that IC died many years ago, probably 20 years ago, and I had to replace it with a modern 7805 high power version chip in the same case and capable of the same performance, 1.5 amps with adequate heat sinking. And that required redoing the wires and moving things around a little bit, and it looks more like a jury-rigged wreck on that one, but this is original, so that's good. The transformer was loose. I tightened up the screws on that, and I did check the overcurrent performance on this, and I was clued into that because, I'll just tell a digressive story here. About the same time I got this, the one we had at work exhibited that the A power supply was dead on it. It developed voltage, but it would not deliver any current. And there's really only two components that are likely to cause that, and that's the current shunt resistor on the circuit board or the associated current bleed or current sink transistor, which is right next to it, and that resistor had cooked off and burned the circuit board around it, and apparently the temperatures damaged the transistor that's, less than a quarter-inch away from it. The resistor's not really supposed to get hot if operated under normal conditions. And there is a current limiting feature in here. It is not a constant current feature, it's just a current limiting feature to make sure you don't go above 1 or 500 milliamps on the adjustable supplies. And the IC has integral current limiting built into it, so there's no external circuit for that. But in the case of the two adjustable supplies, it's done with a transistor and a resistor on the circuit board, and to make it simpler to troubleshoot, you can divorce or segregate the voltage regulator supply circuit from the current limit sensing and activity circuit. I'm just not thinking of the right word, but the circuit that actually handles the current limiting. In order to divorce those from each other for making it simpler to troubleshoot, there's a solder jumper on the circuit board that you can remove. You're supposed to install it during assembly and remove it when you're done testing, or put it back on when you're done testing. And I noticed on that power supply we had at work that when that was assembled, which was actually assembled by the teenage son of a coworker against my wishes. I'd arranged for the thing to be purchased, and I was thinking I was going to build it myself, but a coworker just took it home without asking and had his kid build it. And I actually had to do a lot of troubleshooting on it because the kid made a lot of mistakes. But, it wasn't horrible. It was just a couple things in the wrong place, a couple bad solder joints. Anyway, the kid apparently hadn't read the instructions and hadn't put the solder blobs on the two jumpers, so the current overprotection circuits were never in effect on that power supply. And obviously somebody who would use the supply at some point taxed it with a load more than 500 milliamps, apparently quite a lot more than 500 milliamps, and therefore burned up that one shunt resistor, and in the course fried the adjacent transistor. So I had to replace those parts, but that's not this power supply. It's not even really easy to see on here where the solder blob jumpers are. They're up in this area, but I can't see where it is immediately. Anyway, so basically just clean up a couple of mechanical repairs and inspection of the capacitors, and that was all that was really required to fix this. Alright, overview of the controls, starting with the front panel. Have the power on-off switch here, the meter, which acts as 6 different meters depending on the position of this 6-position switch. It can be volts for the A supply, amps for the A supply, volts for the B supply, amps for the B supply, volts for the 5-volt supply, and amps for the 5-volt supply. The meter is scaled with a red and a black scale. The red one goes up to 5.5, the black one goes up to 20. And the color coding on the switch tells you which scale to look at. So if I'm in volts for A or B supplies, which can go to 20 volts, then it tells me to look at the black scale, and that does go up to 20. If I'm in amps for either of those, these are limited to 500 milliamps, and 5 on the scale represents 500 milliamps. And it should not go up to 5.5, which of course would be 550 milliamps. On the 5-volt supply, it's the volts that are on the red scale, and it's a 5-volt supply, so once again it should go up to 5. And amps, it's a 1.5 amp supply, so you'd go up to 15 on the black scale for that. The 5.5 on here is actually kind of nonsensical because you should never get there. It should be current limited or voltage limited, so it should never get beyond the 5 on the red scale. But I guess I had to put something there because it stopped short of full scale. There's a green binding post for chassis ground. The only things in this power supply which are connected to earth ground coming in on the green lead of the power cord is the chassis, the frame of the power transformer, and this post because it's attached to the chassis. Nothing else is grounded, and nothing in the power supply circuits are earth grounded either or tied to the chassis. They're all totally isolated. For the 5-volt supply, we have red and black binding posts. It's marked 5 volts, 1.5 amps. For the A power supply, 0 to 20 volts, up to 0.5 amps. And then the same thing for the B supply, same limitations spelled out. There is a supply voltage knob, goes from 0 to 20. In reality, it doesn't go completely down to 0, but it's close enough. And the knob was never put on this one quite right. It's you know, it doesn't go all the way up, but the pointers on these knobs are kind of nonsensical. They don't really have anything to point at. You just turn the knob. There's no scaling on them, so they could have just been blank or unlined knobs. The way this works is this is a dual potentiometer here and a single potentiometer here. So normally you would just use the black knobs for A and B, but when you turn the black knob, it is clutched to the red knob and turns it as well. And once again, the pointers don't line up, so that's kind of screwed up. The knobs were not installed very well. But again, it doesn't really matter because they don't actually point to anything. As long as the switch here is in the independent mode, then this knob does the A and the big black knob here does the B. If you move the switch to the right, that's tracking mode, then these two knobs, the black one and the red one, control A and B. With the small knob being A, it replaces this knob in that instance. And this one still controls B, it always controls B. So they kind of indicate that here by saying the big knob is B and the small knob is A, and it tracks B. But it's not electrically or electronically tracking, it's just by virtue of the knobs being clutched together. So assuming you've got them both clutched to the full counterclockwise position, then they always track. So even if you've got it in tracking mode, you can just turn whichever one of these is easier to grab, and both supplies will change by the same amount and stay pretty close to each other. But again, it's not electronic tracking, so it's not like the B supply is actually looking at the voltage supplied by the A supply and matching it precisely. It doesn't work that way. It's a simple clutching of the knobs. So they could be off from each other a little bit. Now, what if you want them to track but be off by an offset? Perhaps you always want the A supply to be 5 volts higher than the B supply. Well, then you could turn the B knob all the way down and then turn the red knob up to the clockwise until you get 5 volts on the meter, and then when you crank the big knob, the little one follows it, and maybe you go up to 5 volts on the big knob, but now the little knob is at 10 volts. So it's always going to be 5 volts more than the other supply, until of course it maxes out at 20 volts, and then it just won't go any higher. So that's the way those are supposed to work. It's not really practical to fix these knobs and make them to point to different things. It's just the way that Heathkit had the inserts pushed in. It's really hard to deal with once they're in there, so I'm not worrying about where they point. So that's the front panel. Here's the back panel, and there's really nothing on it. It has plastic insulator covers for the voltage regulator IC and the two series pass transistors for the A and the B supplies. The transistors and the power voltage regulator IC are electrically isolated from the case, which they would need to be since these are galvanically isolated from each other and from earth ground. The Heathkit name tag, you can still kind of make out the Heathkit on it if you look at it just right, but it's really hard to see. The serial number does survive. I don't know if that's supposed to be an I. It looks like the I on the IP, but it also looks like the 1 on the 18, so it looks like they just used a vertical stroke. It's probably 16-56090. Again, I don't know how to track that. I don't really care anyway. But it's interesting, I always noticed this on the Heathkit labels. They said series number, where they mean serial number. Like, who thought that was reasonable? Series and serial don't mean the same thing, although they have a similar root. It's not a series number. That would be fixed then, and it wouldn't be different for everyone. And these are serial numbers. So there's nothing else on here except where the line cord enters, and the EIA code number, the fact that it's 120 or 240 volts AC, 50 or 60 hertz, uses 90 watts, mentions that it uses a 1.5 amp fuse inside. Here's the bottom. Again, nothing to look here, folks. Go on your way. Just mounting screws for various things, and the voltage selector switch. There we go. It's in the 120 volt position. It always mystified me why Heathkit was so inconsistent in its test equipment with the voltage selector switches. Many of them had switches, but a lot of them were internal, as this is, but you had to open the case to change them. Here you could just go on the bottom. Why weren't they all done that way? It's such a good idea. And a lot of them you actually had to go inside and desolder jumpers and so on. It just seems like for the cost of a switch, they should have all been done that way. So getting to the inside, we have a large 12,000 microfarad electrolytic capacitor. That's the main filter capacitor for the fixed 5 volt supply. It has a dropping or a drain resistor on it to drain it after power is turned off, and a 2-diode full wave rectifier, but not a bridge. And then the IC only requires stabilization capacitor, this disc capacitor down here, and one resistor here. Now this gray thing down here is a current shunt resistor, and that's used so that the front panel meter can read the current being supplied by the 5 volt regulator. But it isn't part of the regulation circuit, it's just part of the current monitoring circuit. We have the mains fuse down here. Here's the inside of the voltage selection switch. Back here we have Q2 and Q1. Those are the series pass transistors for the A and B supplies. Here's the circuit board, which has nothing to do with the 5 volt supplies. It's all about the two adjustable power supplies. And the board is pretty much a clone. The left side and the right side are nearly identical. They only made some slight positional adjustments of some components because the way that the board slides into these plastic slots to hold it in, it just works out with the components on the left side don't have to come very close to the left side of the board, but on the right they do, so they had to move some of them in a little bit to clear the plastic slide, whereas on this half of it those components are arranged a little more generously because they had the room to do it. There's only two adjustments on here besides the adjustment on the meter for zeroing it, and these are maximum voltage adjustment trim potentiometers for the A and the B. So you basically turn the knob on the front all the way up and then adjust these until you get 20 volts. And that's it. That's the only thing you can adjust. There's no calibration for the meter itself. It's all based on the tolerances, the resistors that are associated with it. These black things here are the current shunt resistors. Here's the other one. They're the equivalent functionality of this one here, but these are 1.1 ohms, and this is a 0.1 ohm. It doesn't need to be such a high power resistor because with such a small resistance, it just doesn't drop enough voltage over it to develop any significant wattage. So it's a lower power resistor, whereas the 1.1 ohm resistors here, even though you only go up to a third of the current, it develops a lot more, dissipates a lot more power, and therefore they get hotter and they need to be a higher power type of resistor. There is one wiring harness made by the factory that was included with the kit. So it kind of comes to the back, snakes along here, goes over here, wires break off to go to the circuit board, and then it folds around the front to service the power terminals along the bottom and the potentiometers and the switch. That's all there is. There are a few resistors tacked onto the switch. There's 3 of them, and those are the drop or the series resistors for the voltage mode. So when the switch is in the voltage mode for either of the supplies, it essentially puts the meter across the output of the power supply with a fairly high value series resistor, in series as it would be, with the meter, which itself has a 50 ohm coil. So that's how it gets the appropriate amount of current going through the meter, proportional to the voltage being measured, so that the meter gives the proper readout. Here's the dual gang potentiometer for the B control with the other one tracking, and here's the single potentiometer for the A. Down here is the tracking switch, and down here underneath the meter is the power on-off switch and the neon bulb to tell you that it's turned on. There is no illumination for the meter. Okay, for a demonstration of the power supply in operation, I'm going to start out with the 5-volt supply. I have a couple of test leads connecting it to my DC electronic load, and I'm going to initially set the current to 100 milliamps. So when I turn on the load, it will be adjusting its resistance until I get 100 milliamps pulled out of the supply. Now these leads are really small gauge wires. They're intended for electronic signals, not for power supply use. So since the supply can put out a fair amount of current, we're going to have a substantial amount of voltage drop in these leads. So just be forewarned that the voltage reported at the electronic load will be less than the actual voltage at these terminals. One more thing I should mention about that while I'm on the subject: unlike a couple of other power supplies that I've shown in recent videos, Heathkit was all over the place about whether they had voltage sensing, remote voltage sensing, on power supply models, and it seemed totally irrational. Some very high-end ones like the IP-27 would have no remote sensing, but a lower one like the IP-28 would have sensing, or even the IP-18 or the 2718, or was it the 2728? I think it's the 2728, which is the clone of the IP-18, those had remote voltage sensing, but yet a model like this doesn't have it. Maybe they decided that to add all that stuff in here would just make it too complicated. You know, not enough room on the back panel, and not enough room on the circuit board for the extra components, and so on. Maybe just make it too pricey. But anyway, this doesn't have it, so there's no way to compensate for loss in the leads. So with all that said, I'm gonna put the meter down here to the volts mode for 5 volts, and I'm going to turn on the power supply, and I get my red neon bulb, and the meter's right at 5 volts. And I read 5 volts up here because the load is turned off, so there's no current being pulled from the supply at this moment, therefore there's no voltage drop in the leads. I can switch the switch to amps, and I show there's nothing. Go back to volts. Now I'm going to turn the load on. And we're going to see I've dropped a fraction of a volt already just in those test leads, but it is delivering, well, 0.099. It's delivering 100 milliamps, and the supply has not changed. I can switch to amps, and remember that it goes all the way up to 1.5 amps, so it's reflecting essentially 100 milliamps. This would be 500 milliamps, this would be 1 amp, 1.5 amps. So I'm going to change my load here so I can tweak the, you can see the cursor move there. Now it's under the 1, so when I turn the knob, it's just going to change in increments of 0.1 amp or 100 milliamps. So I'm going to go back here to volts, and I'm going to watch this as I cycle up. 200 milliamps, 300 milliamps, 400 milliamps, 5, 6, 7, 8, 9, 10, that's 1 amp. We're going up, we're at 1.5 amps, and the voltage has moved ever so slightly, well within tolerance. And it is putting out 1.5 amps right on the money, but the voltage has dropped to basically 4 volts here, just due to 1 volt lost in the test leads at 1.5 amps. So I'm going to go and switch to current here, and we can see that we're up to about 1.5 amps. Now I'm going to go down through the ranges: 1400, 1300, 1200, 1100, 1 amp, 900, 800, 700, 600, 500, 4, 3, 2, 1, and no current being drawn. Go back up to 100 milliamps. So that one's working great. And by the way, there is no way to turn off individual supplies on here. There's one power switch. They're all turned on. I've got the voltage mode selected independent. I've got both large knobs turned down. I'm going to move my leads to the A supply. I'm going to select my meter up to volts on the A supply. And it's at 0 because the knob is at 0. So this one actually does seem to adjust down really close to 0. Now I'm going to turn the knob and watch what happens on the meter. I can adjust all the way up, and it's stopping a little bit short of 20, so I'm going to get out my screwdriver and adjust this potentiometer up here until I do get 20. So there we go. So turn the knob, go back to 0, and using this as a meter, it's pretty close to 20. I can tweak it a little bit more to get it right up to 20. And depending how you look at the meter, it's the parallax is there, but it's basically 20. It's pretty accurate. So now I'm going to watch the voltage here and switch in the electronic load. It's set to 100 milliamps. And I could now switch to amps here and see that on the red scale I'm at 100 milliamps. So I'm going to switch back to volts. I'm going to go up in stages of 100 milliamps. That's 200, 300, 400, 500. Voltage doesn't change. Now I'll switch the meter to amps and show that it's reading 500 on the red scale, 500 milliamps. I'm going to go back down on the load, 400 milliamps, 300, 200, 100. So the meter is pretty darn accurate. It's better than some of them I see. And just for yucks, I'm going to take the voltage all the way down until it's 0. Go back to volts, nothing there. I'm going to turn the load off, move my leads, make sure this knob is turned all the way down, put the meter on B volts, turn my load on. It should be pulling 100 milliamps, but I'm at 0 volts, so I'm going to turn this one up to 10 volts. And I'm reflecting up here that it is delivering 10 volts and it's pulling or putting out 100 milliamps, 0.099. Obviously pretty much the same thing. So once again I'm going to mess with the current. 200, 300, 400, 500 milliamps. Doesn't budge. I'm going to switch to amps. I'm up to 500 milliamps. Go back down on the load, 400, 300, 200, 100, and then I'm going to turn the voltage down to nothing. So that is a demonstration of this power supply in operation, and everything is perfect with it. So now an overview of the supply in its fully assembled form. One thing I was never too keen on with this style of case is that they often have a bit of a bow to the top and it's really hard to get out. I've tried it before and it ends up just wrinkling the case and then it sets even more crooked, so I'm leaving it alone. It's a smart looking product. While I do like the new look design, which this IM18 vacuum tube volt ohm meter is an example of that. It has that beige look and that style of knob, and I've restored a number of other pieces of equipment with that same series. But when it comes down to it, I think my favorite look for them is their last look. I forget what it's called. I'll check Chuck Penson's book because it does say what those are called. This blue look, I always thought it was the most professional looking version. Maybe not everybody agrees with me, but it was my favorite Heathkit look of the later years. Not to be confused with some of the real early designs from, say, the 40s, the late 40s. Those looked really handsome too, but you couldn't see that kind of styling being used on anything much more sophisticated than some really simple equipment. It just would have looked out of place. So anyway, so that's the final look at this product. Let's take a look at the manual. IP-2718 manual. Copyright 1976. It's about right. It's the typical Heathkit manual with all the good upfront information for people who are just starting out. The usual detailed and well illustrated and well thought out assembly instructions that anybody capable of following instructions and could really put this together successfully. Lots of good diagrams. You know, and one thing Heathkit did is they definitely spent the money and didn't chintz out by just giving you a little 2-page diagram that only the most advanced users could make sense of. Your operation instruction telling you all the controls and switches and what they do and how to use them. Operating procedures for independent and tracking mode, different applications, independent floating supplies, all of the supplies ganged together in various different ways, sharing the loads with half ohm resistors, not supplied, but that's how you can share supplies in parallel. A nice troubleshooting section. Lots of, if this is bad, check these parts. Charts, specifications, meter accuracy 5% of full scale. I think my observations is it's better than that. Circuit description of the primary circuit and the 5-volt supply and the 20-volt A and B supplies. The circuit board X-ray view, semiconductor identifiers, comparing the Heathkit part numbers with the generic part numbers. Not all of the Heathkit manuals had that or had complete tables. On this one, practically all the transistors are the same, and all the diodes, are, except for 2 of them, are the same. So it makes for a fairly short chart. And the same thing with the transistors and the one integrated circuit. And that's the end of the main manual, but we're not done yet. As Heathkit tended to do in the later days, they weren't content to just have the pages in the manual. They went with the illustration booklets that were larger paper and could be folded out separately from the pages of the manual so you weren't flipping back and forth so much. I'm not even looking at all pages here, but this is the one that just illustrates all the parts when you're doing your initial inventory and assembly. Identifying all the parts that get mounted on the chassis, all the wiring of things on the front panel, and a continuation of that. And then attachment of the wiring harness to the chassis mounted components. Just a diagram of the wiring harness itself. AC power connections. And a diagram of what does what. I'm not sure what that diagram is used for. I'm sure it's useful for something. A table of resistor color codes and how to identify capacitors. So, very useful chart. And last but not least, this is a marked up schematic. This is actually the schematic I borrowed to illustrate how I modified the same kind of power supply I have at my office. I did that probably around 1990, thereabouts. And the LM309 fixed 5-volt regulator that was natural to the kit had burned out or failed or something on that one. And I wasn't able to lay my hands on one, so I used the more modern LM350 and pretty much just used the textbook circuit out of the data sheets and put it in place of that. So I had marked this schematic up with those changes. I always found this schematic to be infuriatingly, well, obtuse is not the word, but almost deliberately confusing. They actually have about 3 or 4 sub-circuits that the draftsman chose to overlay each other, like trying to interleave fingers of 2 hands or 4 hands in this case. You know, there's one circuit that actually has nothing to do with this circuit, but it's shown here, 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 different parts of it interleaved with the circuit that should be in this position, and they do that in a couple other places too. You know, this part up here really shouldn't be there, it should be down here. Just not a good layout. I don't think somebody thought this through very well. So I'm in the process of doing one of my redraws of the Heathkit schematic, trying to improve upon it and make a fresh new CAD drawn version available to anybody who wants it. And I haven't done it yet at the time of this video, but I am working on it. And to that end, I usually, when I'm doing a layout change, not just a neatening up process, I've been experimenting with different layouts, trying to find something that lays out pretty well and makes sense. It's easier to understand how the circuit works. There's a lot of notations on here which kind of clutter it up. This is actually just one of the channels, the A channel. I'm showing B here. A is the same, except that I have a little area dotted here, which is the way it is on B, and then for the A supply it's this somewhat more complicated circuit, and that's for the tracking. And I also have the metering circuit sketched out down here, and I have some theoretical subdiagrams shown here, and then just a sketch out of the 5-volt power supply just stuck down here in the corner. Probably when I redraw this, I'm going to just show the one circuit plus the 2 detailed diagrams to show the differences in the tracking area, and otherwise lay it out more or less like this. If it turns out where I can fit 2 of these on the drawing, then I'll do that, but I don't think I will. Not and have a nice layout that's not too crowded. There's really no point showing the same exact thing twice. And Heathkit helped with that because, at least on these 2 duplicate circuits, all the parts are numbered with 3 digits. So C205, R203, they all start with a 2 after the letter. And that's for the B supply. The part designations are the same with a 1 in place of the 2, so it'd be C105, R113, and so on. So all I have to do is make a notation and say they're the same except as shown, and here's the prefix to the number for the A and B supplies. Okay, so with that in mind, I have a simpler sketch so I can describe the operation of the circuit. So I'm going to start out with the incoming AC supply. This is just the way Heathkit drew it, and there's nothing wrong with this. Got the line cord coming in, hot on the top, neutral on the bottom. The green lead or ground lead is connected to the chassis. They're using the circuit ground symbol here instead of a chassis ground symbol. Probably did that to not confuse people reading it who weren't used to all the different symbols. The power switch is here. The top part of it just switches the power, and then the bottom part switches the sub-circuit that has the neon power on indicator bulb, its current limiting resistor, and it taps into the middle of this 2-winding primary coil. And if you've looked at some of my other schematic dissections, this is a very common way to do it. A lot of the Heathkit supplies did the same exact thing, but instead of a switcher, they just used jumpers to do the same thing. The point is that when you're in 120 volt mode, it's expecting to see 120 volts across each of these coils. So this switch arranges it so they're wired in parallel with each other, and then that parallel combination is across the AC line. If you move the switch to the 240 position, now these have to be in series so that each of them has half the incoming voltage, which is still roughly 120 volts per coil or per winding. And since the neon bulb and its current limiting resistor is calculated for 120 volts, when it's in the 240 volt switch position, this sub-circuit is connected to the middle point between the two windings, so it's getting half of the applied voltage, therefore it's still 120 volts. And other than that, there's the fuse there to protect it, and there's nothing else to it than that. Now I'm going to start with the secondary side, and the 5-volt power supply first. So there's a center tapped winding just for that. It has 2 diodes, which is wired in a full wave rectifier configuration, but not a bridge. I keep running into people who think that if you say full wave, it has to be a full wave bridge, and that's not true. If you have a center tapped winding like this, and you make the center tap your circuit common or ground or whatever you want to call it, then these 2 diodes coming off the outer points in the winding will give you full wave rectification without needing a bridge. There's a capacitor and resistor. The capacitor is 12,000 microfarads, so pretty hefty capacitor. And there's a 220 ohm resistor across it to bleed it down. That's pretty common with larger capacitors, since they can hold a charge for quite a long time. And it's good to put a load across them so when the power is disconnected, it'll drain the capacitor and not leave it with a charge on it. Then there's an IC voltage regulator. Originally it's an LM309. It's a fixed 5-volt regulator. It can only be 5 volts. Unless you play some tricks with it, it is technically possible to offset their reference point and make them more than 5 volts, but natively they're 5 volts fixed. They have an input terminal, an output terminal, and a ground or reference terminal. In this case, the ground terminal is connected to the circuit common. This contains everything to do a complete voltage regulator in one IC, except for the incoming filtering and rectification. The circuit includes built-in overcurrent protection and over-temperature protection. So it's very difficult to damage the chip, even if you abuse it through weird stuff in the connections. But the LM309 is an older chip, which is why I mentioned before that I had already modified one of these power supplies to use an LM350, which is in the same family, but it's an adjustable voltage regulator. It has all the same characteristics otherwise. It just takes a few more parts around it in order to program it to get the desired output voltage. Anyway, so there's this incoming 0.1 ohm shunt resistor. So it's negligible in the circuit, and then the IC regulates the output to 5 volts and is connected directly to the plus 5 volt output terminal, circuit common, to the negative terminal of the 5 volt output. The negative is connected through a 0.01 capacitor to chassis ground or earth ground, and that's there in case there is an AC potential on here. It shorts it to ground, but it's not otherwise pertinent to the circuit. There is a capacitor, 0.2 microfarads across this, and electrically that's kind of like having it here. It is pretty common to have some sort of small capacitance hanging on the output of these 3-terminal voltage regulator ICs. But it's also common to have a small capacitance right across the output terminal of power supplies, so this capacitor sort of fills both bills. Although in reality it's not too useful to this, because this is on the back of the case, this is on the front of the case, and there's all that wiring harness, wiring, there's a foot of wiring or something between here and here, so it's not all that helpful here. Maybe not helpful at all. Anyway, so the only other thing to say about that is, why is this shunt resistor here? Well, when you are operating the meter here in the 5 volt supply amps position, the plus side of the meter is connected here through the violet lead, comes all the way back here, and the violet lead is connected to here. So one side of this shunt resistor through the 150 ohm resistor. The other side of the shunt resistor is the blue lead, and the blue lead comes up to here and therefore is connected to the minus side of the front panel meter. So it's essentially the same as having the meter right between these two wires, as if it was right here. So the amount of current going through the 5-volt circuit drops a small voltage across this, and with this resistor in series, it essentially changes this meter into a small voltmeter. So it's measuring the voltage drop across this shunt resistor and thereby determining what the current through the circuit and out the 5-volt terminals is. Another way of looking at it is that with the 150 ohms added to the integral 50 ohm resistance of the coil in this meter, you've got a 200 ohm resistor essentially across this 0.1 ohm resistor, and therefore 1/2000th of the current that's going through here will also go through this much higher resistance circuit, and that's how it works. So that's, and then if you're measuring the voltage, it's connected similarly, except now it's measuring right at the output terminal going through this 5490 ohm resistor into the plus side of the meter, and then the negative side of the meter is connected directly to the minus terminal. So when it's in voltage measuring mode, the meter's connected right here instead of up here. But otherwise it works the same. Once you figure out the resistance of this resistor and the resistance of this meter, you have a ratio, and the a voltage that's applied to the whole circuit results in a smaller drop across this and an appropriate voltage or appropriate current that gets the meter to swing to the proper position. So very simple, very basic, classic circuit. So here's the rundown on this circuit, but I'm going to start out with the very similar circuit to this. We have a center tapped coil again, center tap winding. The middle of it is connected to some sort of circuit common point, and the outer parts are connected this time to a full wave bridge rectifier with 4 diodes. And the reason it's done that way instead of this way is this one has to develop a positive and a negative voltage, not just a positive voltage. And that's why you need to have the bridge here to get that result. With that in mind, let me jump to, I apologize for the noise in the background. My color laser printer has decided to do a cartridge cleaning process, which takes quite a while. I don't want to wait for it to finish. So this is the same exact circuit without all the extra notations and things on it. And it's laid out for optimum understanding of each circuit module, but it doesn't as accurately represent how they're connected to their respective commons. So you have a positive and negative supply here. Let's start with the negative one. We come off the negative side of the bridge. Immediately we have just a small 10 microfarad capacitor to this symbol, which in the case of this particular diagram is referencing the circuit common point for this particular part of the power supply. It is not chassis ground. It's not the ground of one of the other supplies. It's just the common circuit point for this particular circuit, if that makes any sense. So you essentially have some filtering here. There's a load resistor on it, but the load resistor isn't connected to this point, it's connected to this point. Well, what's the difference? They're functionally the same point, but what they really are is they're on opposite sides of the current sensing shunt. Already discussed how the shunt worked for the 5-volt supply. This is the same deal. Any current coming to the negative terminal of this supply has to come through this 1.1 ohm shunt resistor. On the 5-volt supply it was a 0.1 ohm, here it's a 1.1 ohm resistor. And so essentially it's in the negative path, and the current flowing through the load and back into the negative side develops a voltage drop across that, which is used to measure how much current is flowing through the power supply output. But that's just 1.1 ohm. It's negligible for any purpose except measuring the current. So when you see this diamond shape, it's essentially the same point as this. So just think about it as being the same point. So we got the capacitor, we've got a load on it, and there's an additional diode here which is not rectifying anything, it's just isolating. And then there's a 47 microfarad cap, same reference on it. And why are these capacitors pointing down with their plus? That's because these are on the negative supply. The ground, if you wanted, the circuit ground, is at a higher potential than the negative voltage, which is about negative 36 volts here. So that's why the positive side is pointing down. It's the more positive side. And you end up with a minus 36 thereabouts supply anytime you see this down pointing arrow in the circuit. Similarly, we come out of the positive side of the full wave bridge, and we have this little quick turn on, slow turn off circuit to reduce transients on power on and off. If we just ignore that for the moment, it's got an isolation diode in here, and then it goes up to here, which is a 2200 microfarad filter cap. That's the main filter capacitor for this power supply circuit. And it's got a load on it, 1.5K, just like the other ones did. And why is that diode there? Well, it's there to isolate this part from this part, so you can't have anything flowing backwards. And then this supply gets used for the main regulator circuit, but we're going to ignore that for the moment. It goes through another isolating diode to a 47 microfarad capacitor. It's the same deal as here, an isolating diode and a 47 mic, then the minus 36 volts. Here you've got an isolating diode, 47 mic cap, and plus 36 volts. That's the up pointing arrow. Anytime we see that in the circuit, we know it's the plus 36 point. So we've developed minus 36 and plus 36 with these circuits. Now we also develop a reference, and if you've seen my descriptions of some other Heathkit power supplies I've done recently, they used a totally separate power supply for their reference voltage. It actually had its own secondary winding on the transformer, its own rectifier, its own filtering. On this supply, they didn't do it that way. They just tapped it off the plus 36 volts. So you've got, but otherwise, from this point on, it's very similar to the ones on the other supplies I've dissected. You've got a resistor and a Zener diode. I believe it's a 12 volt Zener diode. And then you have another stage going to a 10 volt Zener diode. So it knocks it down to 10 volts in two stages. And it applies that across this resistor voltage divider. And it's got that diamond on the bottom. So remember, that's essentially the circuit common point, roughly 0 volts in relation to everything else. So you develop that across here. It's 470 ohms to 500 ohms on this trim potentiometer. So you get roughly half the voltage. This is 10 volts, so you have about 5 volts here and 10 volts there. So 5 volts across this. The middle of that is applied to the top of the main voltage controlled potentiometer on the front panel, and the bottom side of it is also at circuit common. So it actually works out so we have about a 0 to 6 volt swing at this point as you turn the pot from one side to the other. So this is our reference voltage, or I'm sorry, it's the reference supply. It's what we're telling the power supply, and the regulator part of the power supply is the voltage we want to be controlling. It's the signal that we're commanding it to do a regulation based on that signal, putting it another way. So let's get down to the actual power supply circuit itself. Already mentioned we have this quick turn on, slow turn off circuit, and we have this other power supply looking thing in here, but it's not really, if you ignore this for the moment. We have this isolating diode, and now we have a 47 mic cap. We have a Zener diode, I don't know what the voltage is, I didn't write it down here. And a resistor across that, and that provides a reference voltage, fixed reference voltage here. And when that is applied to a bipolar transistor in this configuration, it becomes a constant current source. So what this is doing is it's injecting a fixed constant current that comes out here. And it goes through this transistor back to circuit common, and it also goes through this transistor back to circuit common. There's some subtleties here why this one is the circuit common on one side of the shunt resistor and these other 3 points are on the other side of the shunt resistor. I won't even get into the subtleties of why that is, but essentially you've got a constant current coming out and you've got 2 ways for it to get back to common. And what you have here is 2 resistors that are essentially changing. Most of the time this guy isn't doing anything, so you can kind of pretend like it's not in the circuit, and you just have the variable resistance presented by this transistor. How much is it turned on varies its effective resistance, and if you have a constant current coming through here and a varying resistance, you have a varying voltage here. That varying voltage is applied to this Darlington pair of transistors. This is just a smaller transistor on the circuit board with a small heatsink on it. This is the big power pass transistor that's heat sinked to the back of the power supply case. And there's a little 47 ohm resistor tied here. Just helps this work better. If you've seen some of my other teardowns, you'll see the same exact configuration on some of the other power supplies. They have a constant current source. They have a controlling transistor which varies its resistance, and therefore the voltage here, and therefore the voltage here, and then the same Darlington pass transistor pair. And you result with this transistor changing its resistance such that the current flowing from here out to the plus terminal is the desired voltage. Well, how does it know it's the desired voltage? You need to have some feedback for it to be regulated. And this doesn't have any feedback. You're presenting an ideal reference here, and this is going to conduct, but who knows if it's putting out exactly the voltage you want. So that's where the reference supply comes in again, and this resistor divider here. From the plus terminal to circuit common, there's this voltage divider made of 2 resistors. And you end up with a voltage here which is a ratio of the output voltage. It's just knocked down to a lower voltage. It's roughly, well, what is it? It's a bit less than half of the total output supply. And that voltage is strangely about the same swing as the output of the voltage control potentiometer on the front panel. Roughly 0 to 6 volts, roughly 0 to 5.8 volts. So they're kind of in the same ballpark. Those 2 signals come down here, and they go all the way back here, and they go to an error amplifier comprised of 2 NPN transistors connected in this configuration. They're essentially the same thing. The positive 36 power supply voltage, a resistor to the collector, the emitter tied to the emitter of the other transistor, which similarly has a resistance going here, and then a common resistor from the 2 emitters to circuit common. This is the classic differential amplifier. It compares 2 voltages here and here, and depending on whether they match or not, you'll have a different signal here. In this case, it's tapped off the middle of this voltage divider, but it's essentially changing this voltage up or down depending on whether one of these voltages is higher or lower than the other one, and it's trying to find stasis. So it's going to keep jockeying this thing, comparing the signal you're trying to match and the signal that is being controlled, and adjusting until they do match. So you have this variable signal here. It comes through this. This is just a buffer transistor. It doesn't do anything with the signal. And then this is your transistor I touched on before, which changes its voltage. It's the amplifier buffer circuit. This is the circuit common. So depending on what the error amplifier is doing here, it's turning this transistor on or off more or less, and thereby varying its resistance until the control signal up here that's controlling your series pass transistor adjusts it just enough so you get exactly the desired voltage. If the voltage here sags a little bit, now that point on the error amplifier will be a little lower than the reference on the other side. It's going to change this a little bit to compensate. It's going to change this point a little bit and turn this on or off a bit until you once again have the desired voltage here. This is the feedback, or the servo circuit, and that's what makes it a voltage regulator. I mentioned that this supply has overcurrent protection. A couple of other supplies I've looked at recently have constant current, where they can actually reduce the voltage gradually as the current output exceeds the desired maximum amount. So it's a soft roll-off of voltage. This sort of has that, but there's no adjustability for it. And it does work the same way. You have a NPN transistor here with its base to emitter junction, in other words, these 2 points, placed across a shunt resistor. If you look at it, the emitter is on this circuit common, which is on one side of the shunt resistor, and the base through this small 470 ohm resistor is placed on this side of the shunt resistor. So as the current going back through the minus terminal returning to the power supply, as that current changes, the voltage developed across the shunt resistor will be the same voltage that's here to here, and therefore the base to emitter voltage will change. We know that these transistors have a threshold which they don't conduct at all unless you exceed their base to emitter junction voltage. So as the current increases here, as you get up to 500 milliamps and start getting over it, these resistors are calculated such that above 500 milliamps you now have a base to emitter junction voltage here, which is enough to start turning this transistor on. And when it turns on, it starts conducting through this way. Remember this constant current source and how it's able to develop a voltage here based on the resistance change here, and that's controlling the voltage regulator. But that same current, you could steal some of it and make it go this way instead of this way. So as this transistor starts turning on, as the output current starts exceeding 500 milliamps, a little bit of that current gets stolen and goes this way instead of where it should be going. And that skews the voltage here, because now this, with less current going through this way, it develops less voltage, and therefore this point moves a little bit, and what it does is it starts turning off this transistor just a little bit. Therefore its resistance is a little greater, therefore the voltage here is a little bit less, and the current going through it is less, so it holds the output current to no more than 500 milliamps. Of course it's not precise, it probably is a little bit higher. That's just so that if there's any component tolerance issues, it doesn't actually start arresting the current below 500 milliamps. So they have some, safety buffer, so it's a little bit tolerant of slight overcurrents. But essentially, as you start exceeding the desired output current, turns this on, it steals current, it reduces the voltage here, turns these transistors off just a little bit more than they were, and thereby reduces the voltage and therefore the current. and keeps the current to a safe value. So that's how it works, but it isn't adjustable like it is on some of the other supplies. Those have the ability to change how the current here is related to a base to emitter voltage here, so that you can actually dial in where it starts trimming back on the voltage. Here it's just an overcurrent shutdown kind of situation. And there's a jumper on the circuit board that if you're trying to test the voltage regulator circuit, you don't need to be worrying about stolen current here, so you can break that jumper and it's just out of the picture, and then you're just dealing with the straightforward voltage regulator part of the circuit. When that's working correctly, you put the jumper back in, and now you reinstate the protection circuit here. Looking at the metering for this, this is an oversimplification of what's there. It's not exactly like it's shown, but if you're in the current mode, you take the 50 ohm coil of this 1 milliamp full scale meter and you put a series 555 ohm resistor in series with it, and then that's connected across the shunt resistor. This side's to here, this side through this circuit common is the same point as this, so it's just like having it going here. So that's just like the way the voltage or the current was measured on the other supply. The component values are different because the current capacity is different, and you have to adjust it to fit the scale of the meter. Now what about when the meter's in the voltage mode for this supply? Well, now the negative side of the meter is connected directly to the minus output terminal, and through the selector switch on the front panel, the plus side of the meter goes through this high value 19.9K resistor and goes to the plus side of the power supply. So just like on the 5 volt supply, when you're in voltage mode, it's placing the meter directly across the output terminals with only this 19.9K resistor in series with the meter movement. So that is, I think, the entire circuit. I don't think I've left anything out. Going back to this circuit, you can see once again I'm trying to lay it out without having to jump back and forth and thinking about, okay, what does this symbol mean? I'm trying to do it without all those up pointing arrows and down pointing arrows and so on. So I'm trying to do it with bust type symbols for the commons. I'm not sure I'm going to do it that way, but that's the way I'm kicking around. I'm developing the structure of this in a more classical way. You know, here's your constant current source up here. Here's your quick turn on, slow turn off circuit here. Constant current source again. Pass transistors up here. Here's your overcurrent shutdown circuit. This is the transistor which turns on and off to adjust the voltage going into the pass transistors, and its base is driven off of the buffer, which in turn comes from the error amplifier as we looked at before. And I've shown it down here. It's powered off of this sub-circuit with the isolation diode and the 47 mic capacitor. I may relocate that somehow and put it down here. It might be clearer, not sure yet. And then, once again, the bases of the two sides of the error amplifier come over here, and they go up and connect to where they will on the circuit. Yes, the reference circuit is kind of awkwardly stuck up here on the top, but it's just like I showed it on the other sketch. I'm still thinking about how I might redo that if I want to do it this way or try to place that, I don't know, down here somewhere. I'm trying to have not a lot of things crossing each other in this area. This is the main part of the circuit. I like to keep that part with a clean layout as much as possible. So it's a give and take. Still to be determined. Luckily I'm doing it in CAD, so if I want to move blocks around and rearrange them, I can do it pretty easily. I do show the full tracking circuit here, which I didn't discuss before, but all it's really doing is substituting one potentiometer for the other. A potentiometer on one shaft, potentiometer on the other shaft, so that you can do the tracking just based on the coupling or the clutch coupling of the two pots on one shaft when you're in tracking mode. I already discussed the meter down here, and here were the little diagrams I did to prove out that I understood the circuit. This is the 5-volt circuit here, and it shows what's happening in current mode. You've got 1.5 amps maximum coming through here, returning to the IC, the voltage regulator IC circuit, and that's a 0.1 ohm resistor, 150 ohm resistor in series with a 50 ohm meter movement, which makes this like a 200 ohm resistor in parallel with a 0.1 ohm resistor, and you've got that ratio there, and that works out to the same ratio in the current here and the current here, which is how you knock down 1.5 amps to be just a essentially 1 milliamp signal. When you're in voltage mode, again, here's the plus and the minus terminals of the 5-volt supply, and you just have that 5490 ohm resistor in series with the meter movement, and you can do simple Ohm's law on that and see how that works to give you 5 volts should develop 1 milliamp, which is full scale on the meter. Same kind of deal with the 0 to 20 volt supplies. You have the negative supply, so current's returning to the supply. It's going through the 1.1 ohm shunt resistor and back into the common of the circuit. And again, you're putting the 1 milliamp 50 ohm coil meter in series with a 555 ohm resistor, and again you can do simple Ohm's law. This equates to a 605 ohm resistor. Do the math on that versus a maximum of 500 milliamps going through here, and you can see how you get the correct current through the meter. And the voltage, once again, the same thing. It's directly across the plus and minus terminals. This time you have a 19.9K resistor in series with the meter, calculated to get full scale reading at 20 volts on the output terminals. I hope all that was reasonably clear. It sounded clear when I was saying it. I wanted to get back to the constant current source here and the whatever we want to call this thing here, the transient preventing subcircuit. The way the constant current source works is that you need some current going through this Zener diode, and its major current path is this way. There's also the resistor across it and the capacitor across it. Just view those as stabilization for the moment. The point is that you're getting a voltage drop, a constant voltage drop across the Zener diode, and that's impressed across the base and the emitter of this constant current source transistor. Because the transistor's base to emitter junction is held constant and the voltage across this resistor is nearly the same voltage, when you've got a constant current there, the transistor tends to make the current at the collector be essentially the same thing. Constant, if not exactly the same value. For our purposes, it's the same current. Therefore, you have a constant current coming out of here. And what's this guy doing over here? Well, in order to have a constant current here, you need the constant voltage drop here. That requires a current through the Zener diode this way. And that means this transistor has to be turned on. Well, it normally is, being an NPN transistor, because its base is pulled high as soon as you turn the supply on and you start developing a voltage here. And that's filtered just a little bit by this capacitor here. So that's the path. And then when you turn the supply off, the voltage here doesn't have anything to hold it up anymore. This diode here, this blocking diode, I think its main purpose is to prevent this large capacitor here from supplying voltage or current and voltage to keep this transistor turned on. So as soon as you turn this off, even though there may still be a charge here, there's nothing on this side of this diode. Therefore this transistor should turn off, but it's held on briefly by the remaining charge in this capacitor. So they must have tacked this on because they realized that there were some transients on the power supply output when you're turning the supply off, and it was advantageous to add this in here. I think in many ways this is one of the most useful bench power supplies that Heathkit ever came up with. Even though it doesn't have all the features of some of the more advanced models that preceded it, it's still a very handy, well-designed, general-purpose power supply with lots of useful features of the kind that people are actually likely to use. You know, most people will probably never use remote sensing. People will probably never use AC or DC programming on a power supply. Very few will. But they do want and can use on a regular basis a meter with protective current limiting, even if it's not able to operate in a constant current mode. At least it has some protection against overcurrent, short of just blowing a fuse or something. Something with a meter that can show you the voltage and the current. It really, ideally, would be 2 meters, but very few have that. At least the old ones, they typically just had 1 meter, and then you could pick what it showed, and this has that. It has 3 power supplies built in. The 5-volt, relatively high current supply, and the pair of 0 to 20 volt adjustable supplies capable of ½ an amp each. And because they are all galvanically isolated from each other and not connected in any way in the circuitry or through its programming or anything, this would be a very useful power supply if you're working on design or troubleshooting of hybrid or combo analog digital circuitry, especially if you're back in the TTL or 5-volt CMOS era, which is still viable, by the way, in spite of all the 3.3 volt stuff out there and so on. You're working with 5-volt logic, you've got a supply there for it. You're also working with some bipolar op-amp circuits or other analog circuits. You've got it. You've got 2 supplies. They can be connected with this point and this point common to the common point of the circuit, then this becomes the minus voltage and this becomes the plus voltage on a bipolar supply. Or you can power independent circuits with it. And the bipolar mode is one place where the tracking comes in handy on this, because it does allow you then to just adjust both supplies at once. You can also put all of these in series, or any 2 of them in series, any 3 of them in series. If you want to get this to this, this to this, then take your power off of here and here, crank both of these supplies up to 20, you could get 45 volts out of it. No problem. You'd still be limited by the maximum current of any one supply, but that's still pretty useful. Or you can put them in parallel. For that you would set both of these to 5 volts using the meter or monitoring the jacks, and then put them all in parallel, all black leads or terminals together, all red leads together. To do that without overheating the supply or causing a problem due to small voltage mismatches, it's best to have a small shunt resistor, or not a shunt resistor, but a matching resistor. I don't know, 1 ohm or something like that. The manual recommends a value. That would come off of here to your common, off of here to the common, off of here to the common. Then all the blacks would be tied together for the negative side, and they would all be kicking in. Then you'd get 2.5 amps at 5 volts out of this. So that can be done. So again, a very nice, well-designed, conservative, useful power supply.